So moving on to answer the questions below. In the Mimian scan, how many flags are set? And that's 2. Moving on to Nmap advanced port scans. Learn advanced techniques such as null, fin, xmas, and idle zombie scans. Spoofing in addition to FW and IDS evasion. Task 1 Introduction. This room is the third in the Nmap series, part of the Introduction to Network Security module. In the first 2 rooms, we learn about live host discovery and basic port scans. Nmap live host discovery, Nmap basic port scans, Nmap advanced port scans, and finally Nmap post port scans. In Nmap basic port scans, we covered TCP flags, reviewed the TCP three-way handshake to initiate connection. TCP requires the first packet to have the SYN flag set. Consequently, we can tell if a TCP port is open based on the response we receive. Security researchers and hackers contemplate the TCP flags shown in the figure below and explained in the previous room and started to experiment. They wanted to know what would happen if we send a TCP packet which is not part of any ongoing TCP connection with one or more flags set. TCP header RFC793. For instance, an acknowledgement flag is set when you want to acknowledge received data. An acknowledgement scan is likely trying to acknowledge data that was neither sent nor received for the first place. Consider the simple analogy, some coming to you out of nowhere to tell you, yes, I hear you, please continue. When you have said anything, this room explains advanced types of scans and scan options. Some of these scan types can be useful against specific systems, while others are useful in particular network setups. We will cover the following types of port scans: null scan, fin scan, xmas scan, Maimon scan, ACK scan, Windows scan, custom scan. Moreover, we will cover the following: spoofing IP, spoofing MAC, decoy scan, fragment packets, idle zombie scan. We will discuss options and techniques to evade firewalls in IDS systems. We also cover options to get more verbose detail from Nmap. Moving on to answer the questions below. Launch the attack box by using the Start Attack Box button and get ready to experiment with different types of Nmap scans in different virtual machines. So we're going to go ahead and deploy the attack box. Alright guys, we're going to let that load. We're going to hit complete. Moving on to task 3, TCP flags. Nmap supports different types of TCP port scans. To understand the difference between these port scans, we need to review the TCP header. The TCP header is the first 24 bytes of a TCP segment. The following figure shows the TCP header as defined in RFC 793. This figure looks sophisticated at first, however, it is pretty simple to understand. In the first row, we have the source TCP port number, and simple to understand in the first row, we have the source TCP port number and the destination port number. You can see that port number is allocated in 16 bits, 2 bytes in the second and third rows. We have the sequence number and the acknowledgement number. Each row has 32 bits, 4 bytes allocated with 6 rows total, making up 24 bytes. In particular, we need to focus on the flags that Nmap can set or unset. We have highlighted the TCP flags in red. Settings. A flag bit means settings its value to 1 from left to right. The TCP header flags are URG or URG. Urgent flag indicates that the urgent pointer field is significant. The urgent pointer indicates that the incoming data is urgent, and that a TCP segment with the URG flag set is set is processed immediately without consideration of having to wait on previously sent TCP segments. Second one, the acknowledgement flag indicates that the acknowledgement number is significant. It is used to acknowledge the receipt of a TCP segment. Third one, we have the push flag asking TCP to pass the data to application promptly. Fourth one, we have a reset flag is used to reset the connection. Another device such as firewall might send it to tear a TCP connection. This flag is also used when data is sent to a host and there is no service on the receiving end to answer. Fifth one, we have our synchronized flag. Is used to initiate a TCP three-way handshake and synchronize sequences numbers with other hosts. The sequence number should be set randomly during TCP connection establishment. And we have our sixth one. The fin or the center has no more data to send. Guys, moving on to task 2. TCP null scan, fin scan, and XMIS scan. We're going to go ahead and start our machine while our attack box is still loading. Let's start with the following 3 types of scans. We have null scan, fin scan, and XMIS scan. Null scan. The null scan does not set any flag. All 6 flags bits are set to 0. You can choose this scan using the /SN option. A TCP packet with no flag set with no trigger any response when it reaches an open port as shown in the figure below. Therefore, from Nmap's perspective, a lack of reply in a null scan indicates that either the port is open or firewall is blocking the packet. So we have right here a little picture of what it is. Nmap /SN target null, no flag set, case TCP port is open. However, we expect the target the server to respond with a reset packet if the port is closed. Consequently, we can use the lack of reset response to figure out the ports that are not closed, open, or filtered. So let's check this out. We have Nmap /SN target null, no flag sent. So yeah, the acknowledgement and the reset. TCP port is closed. So below is an example of null scan against a Linux server. The null scan we carried out has successfully identified 6 open ports on the target system. Because the null scan relies on the lack of a response to infer that the port is not closed, it cannot indicate with certainty that these ports are open. There is possibility that ports are not responding due to firewall rule. Note that many Nmap options require root privileges unless you are running Nmap as root. You need to use sudo as the example above using the /SN option. Fin scan. The fin scan sends a TCP packet with the fin flag set. You can choose this scan type using the /SF option. Similarly, no response will be sent if the TCP port is open. Again, Nmap cannot be sure if the port is open or if a firewall is blocking the traffic related to this TCP port. However, the target system should respond with a reset if the port is closed. Consequently, we will be able to know which ports are closed and use this knowledge to infer the ports that are open or filtered. It's worth noting some firewalls will silently drop the traffic without sending a reset. Below is an example of fin scan against a Linux server. The result is quite similar to the results we obtained in earlier using a null scan. Moving on to Xmas scan. The Xmas scan gets its name after Christmas tree lights. An Xmas scan sets the fin, the PSH, and the URG flags simultaneously. You can select the Xmas scan with the option /SX. Like the null scan, a fin scan, if a reset packet is received, it means that the port is closed, otherwise it will be reported as open filtered. The following two figures shows that the case when the TCP port is open and the case when the TCP is closed. The console output below shows an example of Xmas scan against a Linux server. The option results are pretty similar to that of the null scan and the fin scan. One scenario where these three scan types can be efficient is when scanning a target behind a stateless non-stateful firewall. A stateless firewall will check if the incoming packet has the synchronized flag set to detect a connection attempt using a flag combination that does not match the SYN packet. Makes it possible to deceive the firewall and reach the system behind it. However, a stateful firewall will practically block all such crafted packets and render this kind of scan useless. Alright guys, moving on to answer the questions below. What three letters represent the reset flag? And that is RST. Next question, which flag needs to be set when you initiate a TCP connection? First packet of TCP three-way handshake, that's SYN. Alright guys, moving on to task 4. TCP, acknowledge, window, and custom scan. This task will cover how to perform a TCP acknowledge scan, a TCP window scan, and how to create your custom flag scan. TCP acknowledge scan. Let's start with the TCP acknowledge scan. As the name implies, an ACK scan will send a TCP packet with the acknowledge flag set. Use the /SA option to choose this scan. As we showed in the figure below, the target would respond to the acknowledge with a reset regardless of the state of the port. This behavior happens because a TCP packet with the acknowledge flag set should be sent only in response to a received TCP packet to acknowledge the receipt of some data, unlike our case. Hence, this scan won't tell us whether the target port is open in a simple setup. In the following example, we scan the target virtual machine before installing a firewall on it. As expected, we could learn which port we are open. And this kind of scan would be helpful if there is a firewall in front of the target. Consequently, based on which acknowledge packet resulted in responses, you will learn which port were not blocked by the firewall. In other words, this type of scan is more suitable to discover firewall rules set and configuration. After setting up the target virtual machine 10.10.176.191 with a firewall, we repeated the acknowledge scan. This time we received some interesting results. As seen in the console output below, we have 3 ports that aren't being blocked by the firewall. This result indicates that the firewall is blocking all other ports except for these 3 ports. Window scan. Another similar scan is the TCP window scan. The TCP window scan is almost the same as the acknowledge scan. However, it examines the TCP window field of the reset packet return on specific systems. This can reveal the port is open. You can select this scan type with the option /SW as shown in the figure below. We expect to get a reset packet in reply to our uninvited acknowledgement packet, regardless of whether the port is open or closed. Similarly, launching a TCP window scan against a Linux system with no firewall will not provide much information, as we can see in the console output below. The results of the window scan against a Linux server with no firewall didn't give any extra information compared to the acknowledged scan executed earlier. However, as you would expect, if we repeat our TCP window scan against a server behind a firewall, we expect to get more satisfying results in the console output. Shown below, the TCP window scan pointed that 3 ports are detected as closed. This in contrast with the acknowledged scan that labeled the same 3 ports as unfiltered. Although we know that these 3 ports are not closed, we realize they responded differently, indicating that the firewall does not block them. Custom scan. If you want to experiment with a new TCP flag combination beyond the built-in TCP scan types, you can do using a / scan flags. For instance, if you want to set synchronize, reset, and fins simultaneously, you can do so using / scan flags rst synfin. So basically you're just putting them all together as shown in the figure below. If you develop your custom scan, you need to know how the different ports will behave to interpret the results in different scenarios correctly. Finally, it is essential to note that the ACK scan and the window scan were very efficient at helping us map out the firewall rules. However, it is vital to remember that just because a firewall is not blocking a specific port, it does not necessarily mean that a service is listening on the port. For example, there is a possibility that the firewall rules need to be updated to reflect recent services changes. Hence, acknowledge and window scans are exposing the firewall rules, not the services. Alright guys, moving on to the questions below. So in TCP window scan, how many flags are set? That's 1. So next one, you decide to experiment with the custom TCP scan that has the reset flag set. What would you add after / scan flags? And that's the RST. Moving on to the next one, the virtual machine received an update to its firewall rule set. A new port is not allowed by the firewall. After you make sure that you have terminated virtual machine from task 2, start the virtual machine for this task, launch the attack box if you haven't done that already. Once both are ready, open the terminal on the attack box and use Nmap to launch an acknowledgement scan against the target virtual machine. How many ports appear unfiltered? So basically this is what you do. You type in sudo nmap /s capital A and your IP address. So I get 4 ports back. So what is the new port number that appeared? That's 443. And next one, is there any service behind the newly discovered port number? And the answer is no. Alright guys, moving on to task 5, spoofing and decoys. In some network setups, you will be able to scan target systems using a spoofed IP address and even a spoofed MAC address. Such a scan is only beneficial in a situation where you can guarantee to capture the response. If you try to scan a target from some random network using a spoofed IP address, chances are you won't have any response routed to you, and the scan results could be unreliable. The following figure shows the attacker launching the command nmap /s spoofed IP machine. Consequently, Nmap will craft all the packets using the provided IP address. The target machine will respond to the incoming packet, sending the replies to the destination IP address. Spoofed IP, for this to to work and give accurate results, the attacker needs to monitor the network traffic to analyze the replies. Nmap/s spoofed IP machine. So here's the example of what it's talking about. So moving on, a brief scanning with a spoofed IP address is 3 steps. Attacker sends a packet with a spoofed source IP address to the target machine. Target machine replies to a spoofed IP address as the destination. Attacker captures the replies to figure out open ports. In general, you expect to specify the network interface/E and to explicitly disable ping scan/PN. Therefore, instead of nmap/spoofed IP machine, you will need to issue this command right here, which I won't be, you could read. To tell Nmap explicitly which network interface to use and not to expect to receive a ping reply, it's worth repeating that this scan will be useless if the attacker system cannot monitor the network for response. When you are on the same subnet as the target machine, you would be able to spoof your MAC address as well. You can specify the source MAC address using //spoof/MAC spoofed/MAC. This addresses spoofing is only possible if the attacker and the target machine are on the same Ethernet 802.3 network or same Wi-Fi 802.11. Spoofing only works in a minimal number of cases where certain conditions are met. Therefore, the attackers might resort to using the decoys to make it more challenging to be pinpointed. The concept is simple. Make the scan appear to be coming from many IP addresses so that the attacker IP address would be lost. Among them, as we see in the figure below, the scan of the target machine will appear to be coming from 3 different sources, and consequently the replies will go to the decoys as well. Nmap/D decoy1 me machine IP. And here's the example of what it is talking about. You can launch a decoy scan by specifying a specific or random IP address after /D. For example, nmap/D 10.10.0.1.10.10.0/me/machine's IP will make the scan of the machine IP appear as coming from the IP address 10.10.0.1, 10.10.0.2, and me, to indicate that your IP address should appear in the 3rd order. Another example command would be nmap/D 10.10.0.1/10.10.02 rdn/rdn, me machine IP, where the 3rd and 4th source IP address are assigned randomly, while the 5th source is going to be the attacker's IP address. In other words, each time you execute the latter command, you would expect 2 new random IP addresses to be the 3rd and 4th decoy sources. Alright guys, moving on to answer the questions below. What do you need to add to the command sudo nmap machine IP to make the scan appear as if coming from the source IP address 10.10.10.11 instead of your IP address, and that's /s 10.10.10.11. Moving on to the next one. What do you need to add to the command sudo nmap machine IP to make scan appear as if coming from the source IP address 10.10.20.21 and 10.10.20.28 in addition to your IP address? So basically what you'll do there is /d 10.10.20.20 comma 10.10.20.28 Moving on to task 6, fragmented packets. Firewall. A firewall is a piece of software or hardware that permits packets to pass through or block them. It functions based on firewall rules summarized as blocking all traffic with expectations or allowing all traffic with expectations. For instance, you might block all traffic to your server except those coming to your web server. A traditional firewall inspects at least the IP header and the transport layer header. A more sophisticated firewall would also try to examine the data carried by the transport layer. IDS, an intrusion detection system, inspects network packets for select behavioral patterns or specific content signatures. It raises an alert whenever a malicious rule is met. In addition to the IP header and transport layer header, an IDS would inspect the data contents in the transport layer and check if it matches any malicious patterns. How many you can make it less likely for a traditional firewall IDS to detect your Nmap activity. It is not easy to answer this. However, depending on the type of firewall IDS, you might benefit from dividing packets into smaller packets. Fragmented packets. Nmap provides the option /f to fragment packets. Once chosen, the IP data will be divided into 8 bytes or less. Adding another /f/f/f or /ff will split the data into the 16-byte fragments instead of 8. You can change the default value by using the //mtu. However, you should always choose multiple of 8. To properly understand fragmentations, we need to look at the IP header in the figure below. It might look complicated at first, but we notice that we know most of its fields in a particular notice. The source address taking 32 bits, 4 bytes on the 4th row, while the destination address is taking another 4 bytes on the 5th row. The data that will fragment across multiple packets is highlighted in red to aid the reassembly on the receipt side. IP uses the identification ID and fragments offset shown on the 2nd row of the figure below. Let's compare running sudo nmap /s/p 80 10.20.30.144 and sudo nmap /s /p 80/f 10.20.30.144. As you know by now, this will use stealth TCP and synchronized scan. And the first 2 lines, we can see an ARP query response Nmap issued an ARP query because the target is on the same Ethernet. The second 2 lines show a TCP CMP ping and reply. The 5th line is the beginning of the port scan. Nmap sends a TCP SYN packet to port 80. In this case, the IP header is 20 bytes and the TCP header is 24 bytes. Note that the minimum size of the TCP header is 20 bytes. With the fragmentation request via /f, the 24 bytes of the TCP header will be divided into multiple of 8 bytes. with the last fragment containing 8 bytes or less of the TCP header. Since 24 is divisible by 8, we got 3 IP fragments. Each has 20 bytes of IP headers and 8 bytes of TCP headers. We can see the 3 fragments between the 5th and 7th line. Note that if you added /ff or /f/f, the fragmentation of the data will be multiple of 16. In other words, the 24 bytes of the TCP header in this case would be divided over 2 IP fragments, the first containing 16 bytes and the second containing 8 bytes of the TCP header. On the other hand, if you prefer to increase the size of your packets to make them look in, you can use the option //data/length num, where num specifies the number of bytes you want to append to your packets. Alright guys, if the TCP segment has a size of 64 and /ff option is being used, how many IP fragments will you get? And the answer is 4. Task 7. Idle and zombie scan. Spoofing the source IP address can be a great approach to scanning stealthy. However, spoofing will only work in specific network setups. It requires you to be in a position where you can monitor the traffic. Considering these limitations, spoofing your IP address can have little use. However, we can give it an upgrade with an idle scan. The idle scan or zombie scan requires an idle system connected to the network that you can communicate with. Practically, Nmap will make each probe appear as if coming from the idle zombie host. Then it will check for indicators whether the idle zombie host received any response to the spoofed probe. This accomplished by checking the IP identification IP ID value in the IP header. You can run an idle scan using Nmap /si zombie IP machine IP, where the zombie IP is the IP address of the idle host. The idle zombie can require the following 3 steps to discover whether a port is open. 1. Trigger the idle host to respond to so that you can record the current IP ID on the idle host. And 2. Send a synchronized packet to a TCP port on the target. The packet should be spoofed to appear as if it was coming from the idle host. Zombie IP address. 3. Trigger the idle machine again to respond so that you can compare the new IP ID with the one received earlier. Let's explain which with figures in the figure below. We have the attacker system probing an idle machine, a multifunction printer. By sending a syn/act, it responds with the reset packet containing its newly incremented IP and ID. This right here is just an example of what it was talking about. The attacker will send a synchronized packet to the TCP port. They want to check on the target machine in the next step. However, this packet will use the idle host zombie IP address at the source. The scenarios would arise in the first scenario shown in the figure below. The TCP port is closed, therefore the target machine responds to the idle host with a reset packet. The idle host does not respond, hence its IP ID is not incremented. You can see the attacker IP sourced from zombie IP. It's sending the reset right here. There's no reply back. Attacker system sends to a target machine a synchronized packet spoofed and sent by the idle machine. Case port is closed. In the second scenario, as shown below, the TCP port is open, so the target machine responds with a synchronized /acknowledge to the idle host zombie. The idle host zombie to this unexpected packet with a reset packet, thus increments its IP address and ID. So, as you could see, sends synchronize, acknowledge, and this right here replies back with a reset. Attacker sends to target machine a synchronized packet spoofed as sent by the idle system. Case port is open. In the third scenario, the machine does not respond at all due to firewall rules. This lack of response will lead to the same results as with the closed port. The idle host won't increase the IP ID. For the final step, the attacker sends another synchronized acknowledge to the idle host. The idle host responds with the reset packet, incrementing the IP ID by 1 again. The attacker needs to compare the IP ID of the reset packet received in the first step with the IP ID of the reset packet received in the third step. If the difference is 1, it means the port on the target machine was closed or filtered. However, if the difference is 2, it means that the port on the target was open. It's worth repeating that this scan is called an idle scan because choosing an idle host is indispensable for the accuracy of the scan. If the idle host is busy, all the return IP IDs would be useless. Alright guys, moving on to task 8, getting more details. You might consider adding / reason if you want Nmap to provide more details regarding its reasoning and conclusion. Consider the two scans below the system. However, the later adds / reasons. Providing the / reason flag gives us the explicit reason why Nmap concluded that the system is up or a particular port is open. In this console output above, we can see that the system is considered online because Nmap received ARP response. On the other hand, we know that the SSH port is deemed to be open because the Nmap received a seen ACK packet back. More detailed output, you can consider using /v for verbose or output for /vv for even more verbosity. And right here it's showing that. If /vv does not satisfy your curiosity, you can use /d for debugging details or /dd for even more details. You can guarantee that using /d will create an output that extends beyond the single screen. Alright guys, moving on to answer the question below. You discovered a rarely used network printer with the IP address of 10.10.5.5 and you decided to use it as a zombie in your idle scan. What argument should you add to your nmap command? So what you will do in this situation is you'll do lowercase s, capital I, 10.10.5.5, and you'll just go ahead and click the green button, and there you go. Alright guys, now moving on to answer the question below. So we're going to launch the attack box if you haven't done so already. If you make sure that you have terminated the virtual machine from task 4, start the virtual machine for this task. Wait for it to load completely the open terminal on the attack box and use nmap with nmap /s, capital S, /f, space / reason 10.10.25.68 to scan the virtual machine. What is the reason provided for this stated ports being open? So basically what I'm going to do is I'm going to copy paste this right here if it lets me. Now I'm gonna paste it right here. I'm gonna hit enter. So now I'm gonna check for the reason, and that's SynAct right here. So basically what I did, I just copy pasted that into that, clicked next, and click the green button, and there you have it. That's the correct answer. So now moving on to the final room, task 9 summary. This room covered the following types of scans: port scans and example commands. So we have the TCP null scan, which is right here, sudo nmap/sn and the IP address. TCP fin scan, which is sudo nmap and it's /sf and the IP address. Then we have TCP xmin scan, which is sudo nmap/sx and the IP address. Next we have TCP mamin scan, sudo nmap/sm. Then we have TCP acknowledge scan. So we have TCP nmap/sa. Then we have TCP Windows scan, which is sudo nmap/sw and the IP address. Then we have custom TCP scan, sudo nmap/scan flags. Guys, I'm just gonna let you go ahead and pause the screen at this moment, and yeah, but other than that, we've completed mostly everything today. Moving on, these scan types really rely on setting TCP flags in an unexpected way to prompt for ports or for a reply. Null, fin, and X can provoke a response from closed ports, while Mimin, Act, and Windows scans provoke a response from open and closed ports. We have /reason explains how Nmap made its conclusion. We have /v verbose. We have /vv for very verbose, and /d debugging, and /dd for more details for debugging. Moving on to answer the question below. Ensure you have taken notes of all Nmap options explained in this room. Please join the Nmap port scans room, the last room in Nmap series. And now we're going to click completed, and voila guys, we have completed the next room, and we'll see you on the next one.